So here's our diagram on this one. This time we're going from 0 to 12, so we're going to use all of these. But since we are using a right Riemann sum, so since we're using RAM, the kind of shorthand rule of thumb that I had yesterday was that we should be using for RAM, since we're always going to choose the rightmost endpoint, we're going to use all of them except for the leftmost endpoint. So we're going to use all of them except the y-coordinate at 0. So here's what your picture should have looked like. So I just plotted the points. I drew kind of a trend of a curve. Right? You didn't have to draw the same thing I did. But then we choose the rightmost endpoint as our rectangle. Rightmost endpoint, and so on for our rectangle. RAM sub 5, there's a total of 5 rectangles here. And each of them is going to have a different base to it. From 0 to 2, that means my base ended up being 2. From 2 to 5, that means my base ended up being 3. From 5 to 7, my base is 2. From 7 to 11, base is 4. From 11 to 12, base is 1. And then we're going to always choose the point that's on the far right, since we're doing a right Riemann sum. So since if we're choosing between 0 and 2, we're going to choose 2. If we're choosing between 2 and 5, we're going to choose 5. Between 5 and 7, we're going to choose 7. For a right Riemann sum, that means we're choosing the right endpoint. And there's the y-coordinates plugged in. That's from the table. Multiply, add. And we get 19.3. So draw the diagram, draw your rectangles. The only difference between this problem and the problems that we were doing yesterday and Monday is that the bases changed with each one. So we couldn't just factor a base out and not worry about it the rest of the time. But the base is always going to be your x distance. The height is going to be your y-coordinate. And which y-coordinate you use depends on whether you're using left, right, or midpoint. And the problem will tell you which one to use. Or, especially on your homework, you might do all 3. Just so that you can see what all 3 look like. So, questions on that before we move on? Okay. Here is the idea of how we get from this to actually getting the area underneath the curve is what we're doing. Region R refers to the area enclosed underneath the function, underneath this function. You don't need to write this down. Just watch. So let's say we have this function, and we could use rectangles to approximate this area. Since we're going from 0 to 2, you might, we did something pretty close to using 4 rectangles when we were doing these kind of problems. And so we could draw out these rectangles. So here would be left endpoint. Something like that. And that could give us an approximation. But the idea is that the more rectangles we would use, the better our estimate. So if we use 10 rectangles, here's LRAM, MRAM, and RRAM. If we took 50 rectangles and put them in here, right, between 0 and 2, then there's our answer. If we put 100 rectangles, so each rectangle has a width at this point of 1/50th. Very small, lots of adding up to do. You wouldn't actually do that calculation of 100 rectangles. But you'll notice that as we go forward here, 500 rectangles, you might start to suspect what the answer for the actual area is. Any guesses? How about 1.3? How about even closer? 1.3 repeating, which would be 4/3. 1 1/3. If you got your fractions down there. So just to give a visual of what that looks like. So here's a few rectangles. And watch that as each of these is still using rectangles. But as we get more and more rectangles, it's going to be almost indistinguishable from just seeing the area underneath the curve. So it's still rectangles, but the rectangle width is so tiny that it starts to look like just that area underneath the curve. And so letting that number of rectangles get larger and larger and larger, that sounds like a limit, will give us the actual area. And that actual area, that actual answer, is what we're going to start to use in the next couple of days. And that is going to be the actual answer is going to be called a definite integral. And let me just break down some of the terminology and what each number and what each thing means. Okay? So let's take a notation. And again, you don't have to write a ton down, but do flip to the back page so that you can see what the integral looks like. It's going to look like this kind of S-shaped figure. And I'm going to give a couple of kind of technical names that you're not going to really need to have like stuck in your head, but so that you have them. A and B are called the bounds of integration. They're the endpoints. So this graph we said, that's up here, we said was from 0 to 2. And so you would put a 0 down here at the bottom and a 2 up here at the top. Kind of like our sums that we were looking at before. On Monday, remember, our sums had usually started at 1 and then went up to a certain number. It's the same idea for the integral. Because the integral is basically a sum that where the number of things we're adding up goes to infinity. So that's why it feels very much like a sum. This bit, the technical name for it is the integrand. It's the function. In terms of the Riemann sums that we were just doing, it's our height. Right? The y-coordinates ended up being our heights. dx. We need to make sure that we put this at the end of any integral we write. It's kind of our, if you think about this integral symbol as an open parentheses, the dx is our closed parentheses of an integral. This is used to stand for the base, which we are saying is infinitely small. Right? We are letting it be infinitely small. And so we don't really need to worry about it anything calculation-wise. We just need to make sure we're writing it. So those are the pieces that make up an integral. You're going to say, here's where I'm integrating from. Here's where I want the area from here to here. And then it is still my base times height for my rectangles. It's just that I have an infinitely small base and infinitely many heights. So how on earth are we going to add all those up? Well, we'll talk about that on Thursday and Friday. But today we're going to talk about some properties that should hopefully make sense. There are 5 properties that are there, and we're going to kind of talk about a couple of them. And I'm going to use areas to talk about them and make sure that we understand how these work. Okay? So this is property number 1. Integral from 5 to 5 of f of x dx. So let's say that this is 5. So let's say that a is 5. And we'll use b being 10, just for the purposes of this. I'm just picking numbers. So if this is 5, if I start at 5, and then I end at 5, how much area is there between 5 and 5? None. There's no area between 5 and 5. And so if I have starting at 5 and ending at 5, in other words, starting and ending at the same endpoint, it doesn't matter what function I'm integrating because there's no area there, because there's no space to find the area of. This answer is going to be 0. When we come across this in examples, usually I'm going to start by saying the integral of 5 from 5 to 5 of who cares, because the answer is 0. All right. the next property that you see in front of you. The next property that you see in front of you. Integrating from 5 to 10. All right? Of f of x dx. Okay? So that means we take and we accumulate this area going across. Like that. And we start to add up these rectangles. So we have these infinitely tiny bases and these infinitely tiny heights that we're adding together. But let's say we say to start at 10 and move to the left over to 5. Right? So our lower bound is 10 and our upper bound is 5. Well, that means that we are moving backwards. And we still have our heights, but our bases are moving backwards. So we need some way to designate that our area is kind of traveling backwards. So we are going to say that these are going to be the opposite of each other. And so that's property number 2 that you have in front of you. So the integral from b to a is going to be the same as the negative integral from a to b. And that's going to be useful because sometimes you'll see the bounds switch like that, or we will want to switch the bounds. And so if we ever switch where a and b goes, we can do that. We just need to make the answer negative from what it was before, because the area is traveling the other direction. Question?
Which one is does it matter which one is the lower bound, or like which letter?
Usually we want our lower bound to be on the bottom and our upper bound to be on the top. But this is saying we can do it the other way. It's just if we switch them, then it has to be negative. Usually we're going to want to go from left to right, because that's just the way we usually read across. All right. Property number 3. Let's take another number. Let's say 7. Okay? And this is going to be useful because sometimes it's going to be difficult to find the entire area from 5 to 10. And it's going to be easier for us to think about the area in little pieces instead. And so let's take at 7. What this is saying is let's take 7 as an in-between point to split our area into. And now we have 2 chunks of areas. This area in blue here is the area from 5 to 7. And this area in green here is the area from 7 up to 10. And what I'm saying is that if I add up the area of this blue piece and the area of this green piece, then we get the entire area. So in other words, property number 3 says that I can split my area into smaller pieces of area and add them up and get the whole area. Right? And we do this when finding other areas all the time. Like if I gave you this shape and said find the area of it, what you commonly might do is give me a split here and say, okay, this is a rectangle plus a triangle. Same idea here, just in a fancier way. I'll skip number 4. It's hard to show visually, but the integral of the sum is the sum of integrals. I'd have to draw another function here. I might show that another time. But property number 5 is, let's say, multiplying the function by a constant. So think about what multiplying the function by a constant is going to do. So let's say I take this, and now I want 2f of x. What's going to happen to all the y coordinates? By how much? They're going to double, right? And so I have the same base I had before, but now I have double the height. So same base times double the height means double the area. And so if I have a constant, then I can just take that constant and bring it out in front. So watch this in action here. So we are not usually going to do an integral this way. But let's say we know these 3 values for the integral. And we want to use it to find this larger integral. What we could do is we could break it into chunks by saying that negative x squared plus 4x minus 3, first of all, integral of a sum is the sum of the integrals. So instead of trying to talk about the integral of all this at once, I can split it into my x squared term, my x term, and my constant term. Like that. But I don't have an integral for negative x squared or 4x. I have an integral for x. And so if I have the integral of x, and I want to know about 4x, well, this is a constant. And the property I just talked about is that I can take this constant and bring it out in front. So what we could do is we can take all the constants and bring them out in front. I'm treating negative 3 as a constant because if there's nothing here, base times height, if my base doesn't have something out in front of it, that must mean that the base is 1 for multiplying. So when it says the integral from 1 to 3 of dx is 2, that's what we mean. And so now we know what these integrals are. This one is 26/3. Give it to us up here. This one was 4. This one was 2. And so we can multiply all that out, and hey, the answer is 4/3. So this is just, this is not the way we're usually going to do integrals. It's just an exercise in using our properties. That we can add and subtract our integrals, that we can take a constant and bring it out in front. All of these different ideas. All right. I got one more problem to leave you with. So find a space on your paper to write this one down on. Where is it? Maybe I have this problem. Ah, here it is. I will give this answer tomorrow, but I want you to try it. Y equals 4x, the area from 0 to 6. So in other words, I want to know what the integral from 0 to 6 of 4x dx is. And I want you to figure it out visually. So draw a picture, draw a graph of what 4x looks like from 0 to 6, and see if you can figure out what the area is going to be. I'll give you a hint. This is not a calculus question. This is a geometry question. It's going to turn into a geometry question.